All right, well, welcome back. So we're going to take a break from trees for a little bit and talk about something related to trees, but a little different area. We're going to talk about dynamic programming. And it's almost New Year's, and I think my resolution this year is going to be to wear more hats. So I'm going to get some practice here. So dynamic programming. We've seen a few times now that some functions can be written recursively, and it's very natural to do so, but the recursive solution may not be the most efficient. And the classic case of this is, calculating Fibonacci numbers. So if we want to calculate the 6th Fibonacci number, we need to calculate the 5th and the 4th. And to calculate the 5th, we need the 4th and the 3rd. And the 4th requires a 3rd and the 2nd, and the 3rd requires a 2nd and the 1st. And Fibonacci 1 and 2 are our base cases. And so our call tree might look like this. So to calculate the 6th number, we need the 5th and the 4th. And to calculate the 4th, we need the 3rd and the 2nd. And to calculate the 3rd, we need the 2nd and the 1st, and so on. So if you look at this, we actually make a recursive call to calculate the 3rd Fibonacci number 1, 2, 3 times. And the 4th Fibonacci number we calculate twice. And so we've observed that if we were to save our results from these recursive calls, once we've calculated the 3rd Fibonacci number here, we don't need to do so here, so we can get rid of this part of our tree, and similarly this. And if we calculate the value of the 4th Fibonacci number here, we can get rid of this part of our tree. And if we were trying to calculate, the 8th Fibonacci number, we would need the 7th and the 6th. The 7th would need the 6th and the 5th. Well, once we go down this whole tree to calculate the 6th Fibonacci number, which is all of this work, we could get rid of that call. So the idea is we're going to save our values when we calculate value for this function, and then when we call this function to calculate the value for some argument, we'll check to see if we've saved the value first. So we might write something like this: Fibonacci n, and we might have an array in memory. We can call it a cache, and maybe we've got 1,000 entries in there, and maybe we'll initialize it to zeros. And we know our Fibonacci numbers are always positive, so what we're going to do in the beginning of our Fibonacci function is we're going to say if cache bracket n is bigger than 0, we'll just return the value that we saved in our cache. So first thing we're going to do in our Fibonacci function, we're going to check this array of saved values, this cache. And if the value at index n is positive, we know that we've saved a value there, we'll just return that value. Otherwise, do the expensive recursion, and we'll get our answer. And at the end, we're going to say return answer. But before we do that return, we're going to save the answer in our cache. So we're going to say cache bracket n equals answer. And we'll note that we're saving this for next time. And then we'll go ahead and we'll do our return. So the first time that we try to calculate fib 6, it's not going to be in our cache. We're going to do, whatever we have to do recursively, which might take a lot of time. But at the end, once we've calculated that value, we're going to save it in cache bracket 6. So in this case, when we need to calculate the value of fib 6 again, first thing we'll do, we'll check to see if cache 6 is positive. It will be, because we'll have saved it before, so we'll just read the value from the cache and return. So this is a way that we can prune our tree and cut out our recursion, and this is called dynamic programming. And dynamic programming works well in cases where we have two characteristics to our algorithm. So the first characteristic is what we can call optimal substructure. And optimal substructure means we can solve a problem by looking at subproblems. So Fibonacci series are not an optimization problem, but we're going to work with a set of optimization problems where we're trying to find the best solution to a problem. And optimal substructure means we can find that best solution by finding the best solution to smaller problems first and then putting those together. So that's going to be one characteristic that's useful, and the other is what we call overlapping subproblems. And that's what we're seeing here in the case of Fibonacci numbers. We're seeing that we keep solving the same smaller problems again and again and again. So in a situation where we can break our solution into subproblems and solve our whole problem by solving those subproblems, and we find that we keep bumping into the same subproblems over and over, that's a case where dynamic programming is going to work really well for us. So I want to explore a series of problems related to this. The first one being the knapsack problem. And the idea of the knapsack problem is, imagine you're like the millionth customer at a store and they are having a big celebration to advertise this, and so for their celebration they give you a bag, and this bag can hold 20 pounds worth of stuff, and they say, okay, you can run around the store, put anything you want in the bag up to 20 pounds, right, and you get to keep it. So it's an advertising thing, right? So what would you put in your bag if you could put in 20 pounds of anything that you wanted? And it depends on what the inventory is that you can choose from. Now, if you're in a computer store, right, you probably would not want to buy, I don't know, an LCD monitor, right, because they're pretty heavy. You might want to buy little micro SD cards, right, because a terabyte micro SD card is worth, a few $100s, and it weighs almost nothing. You probably would not want to buy a lot of books, because books don't really get you a lot of value per pound. So if our goal here is to maximize the amount of money that you can store in this bag, right, the total amount of value, you want to look for things that are worth a lot of money and don't weigh a lot. And so we can imagine that we have an inventory of items. So let's suppose we have an item, a weight, and a value. And here's item A, and let's say it weighs 2 pounds and is worth $2. Here's item B, and it weighs 3 pounds and is worth $9. And here's item C, and it weighs 4 pounds and is worth $10. All right, so how would we pick items to put into our bag? And suppose that our bag has a capacity of 5 pounds. So what items should we put into our bag? Well, our goal is to maximize the total amount of value we put in our bag. And you might say, hey, let's start with the most valuable item. That would be item C. So if we put in 1 of item C, the total weight that we put into our bag is 4, and the total value we've got in our bag is 10. Well, our bag can hold 5 pounds. We've put in 4 pounds. We could still put in 1 pound worth of extra stuff, but there are no items that weigh 1 pound. And so if we start by putting in just our most valuable item, which is C, we get a total value in our bag of $10. But if instead we put in 1 of item B and 1 of item A, that would weigh a total of 5 pounds, and the value would be 9 plus 2, which is 11. So this is a more optimal solution. We get a higher value in our bag by putting in these less valuable items. So picking the most valuable item to start with does not get us an optimal solution. Now, we could say, hey, you know, if we look at the value per weight, this is $1 per pound, this is $3 per pound, this is 2.5 per pound. We should have started with the item that had the greatest value per pound. So we can try that as an algorithm, and let's imagine we have an inventory like this. So here's the weight and the value. So item A weighs 2 pounds and is worth $1. Item B weighs 3 pounds and is worth $9. And item C weighs 4 pounds and is worth $13. And suppose the capacity of our bag is 10 pounds. Okay, so we can calculate value per weight. And you know, this weighs 2 pounds is worth 1. This is only 0.5 per pound, not very valuable. Item B, 9 divided by 3, that'll be worth $3 per pound. And item C, $13 for 4 pounds, that's worth $3.25 per pound. So this is our most valuable item. So let's start by putting in item C. And we can put in 2 of those, right, because our capacity is 10, so we'll put in 2 of item C. And that's 8 pounds. So weight equals 8. And the value will be 26. And since our capacity is 10, we've got 2 pounds left over, so we can go ahead and put in item A. So we'll put in 1 of item A. That weighs 2 pounds and has a value of 1. So we've got 10 pounds in our bag and $27 worth of value. But again, that is not the optimal solution. We can do better by putting in 1 of item C. The weight is 4, the value is 13. Well, that weighs 4 pounds, and then we can put in 2 of item B, and that'll be a total of 6 pounds, and the value of that is $9 each, so this will be plus 18. So we've got 10 pounds in our bag and $31 worth of value. This is a better solution. But to get this solution, after we put in our first item C, we need to choose an option that is not using our most valuable item anymore. We need to take an item that's worth slightly less because it will leave us more space for a second one of these items. So if we can solve a problem by just trying to find the most optimal solution at each decision point, for example, if we can just say, let's take the most valuable item per pound, or let's just take the most valuable item, period, right? That's an algorithm where that works is called a greedy algorithm. And greedy algorithms are pretty easy to code. And there are a lot of algorithms that work well with this greedy approach. When we look at Dijkstra's algorithm in a future lecture, it's a path for finding, an algorithm for finding shortest path through a graph. That'll be an example of a greedy algorithm. But for the knapsack problem, greedy algorithms don't work. All right. Now also, it's understood that we cannot split an item in half. Right? If we have 1 pound left in our bag, we can't split item A in half and take half of item A. So this is sometimes called the 0-1 knapsack problem. And so we either take an item or we don't take an item. And we can take as many of each item as we want. There's no limit to the inventory. But we can't take a fraction of an item. Now, if we could take a fraction of an item, then this approach of picking the item that's most valuable, that would be our best solution. That's a greedy approach, right? We could simply take as much of this item as possible. We could take 2.5 of this, and that would get us a total value of 26 plus 6.5, 32.5. That would be our best solution. But in this 0-1 knapsack problem, where you have to take a whole number of items, greedy approaches don't work. So how can we solve the knapsack problem? So let's imagine that we have an inventory And so we have weight bracket I, and we have value bracket I, and this is the weight and value of the ith item. So there's some kind of inventory storage in our system. And let's imagine a function called maxval. And the idea of maxval is you call this function, you say how much weight can you store in your bag, and it should return the maximum value. So it solves this knapsack problem. And to write this function is pretty straightforward if we think about the problem a little differently. So what we're going to do is, let's suppose we have n items. So we have n items to choose from. Well, whatever collection of items gives us our maximum value, we know that it contains at least one item, and that first item that we put in our bag is either item 1, 2, 3, 4, up to n. The order in which we put these in our bag doesn't matter, right? Because we're only concerned about the total weight. So there are only n possibilities, right? So the first possibility is start with item 0. We index from 0. The next possibility is we could start with item 1 or item 2 all the way up to item n-1. And one of these situations will lead to a maximal value. Now, it could be that 2 or more of these give us the same maximal value, but whatever's going to get us the maximal value, at least one of these is going to get us there, because we have to start with some item, right? All right, so here's how we think about this. Suppose we start with item 0. Well, what we have in our bag is the value of item 0. And then what we have left as far as capacity for our bag is the original capacity of our bag minus the weight of item 0. So if we start by putting item 0 in our bag, we get this much value, and we have this much space left in our bag. So what's the maximum value we can get from that reduced capacity? Well, that's just maxval of that reduced capacity. So the total value we can get if we start with item 0 is the value of item 0 itself plus whatever the maximum is we can get from this diminished capacity, the capacity of the original bag minus the weight of item 0. But if we start with item 1, we get the value of item 1 plus the maximum value of our capacity minus the weight of item 1. And if we start with item 2, the maximum value we can get is the value of item 2 plus whatever the maximum value is we can get from a bag whose capacity has been reduced by the weight of item 2. And in our last case, if we start with item n-1, we get the value of item n-1 plus whatever the maximum value is we can get from starting with a bag whose capacity has been diminished by the weight of item n-1. We have to start with some item, either item 0, 1, 2, 3, 4, up through n-1. And depending on which item we start with, this is the maximum value we can get out of our bag. So we just find the maximum of these, and that's max value of capacity. So it's a different approach to solving a problem, right? we break it down into n possibilities, and for each of those we find the maximum value by using the max_val function. But notice the max_val here is smaller, the capacity is smaller than the original capacity. This is the subproblem aspect, right? So we find the maximum value for each of these cases added to the value of the ith item, and whichever one of those gives us the largest value, that's the maximum value for capacity. All right, and there's one caveat here. If you're actually coding this, there's one thing we need to be careful of, which is if the weight of item 0 is bigger than the capacity of the bag, we're not allowed to say, well, let's put item 0 in our bag, because it won't fit. So we need to make these conditional. So if weight of 0 is less than or equal to capacity, then we can say, okay, we can get this value. Here, if the weight of item 1 is less than or equal to our capacity, then we can get this value. If the weight of item 2 is less than or equal to our capacity, we can calculate this value. And if the weight of item n-1 is less than or equal to capacity, then we can calculate this value. But we're not allowed to calculate these values and consider them if our item weighs more than our capacity that we're starting with, because we'd get that value, but we'd break our bag because our item weighed too much. So we only calculate these where the weight of the item is smaller than the capacity, and then we find the maximum of those. So this gets us a solution to the knapsack problem. It's guaranteed to work, but it's potentially very inefficient. So let's go back to a sample problem where we had just an inventory of 3 items, and let's see how this works out if we want to find the maximum value for a bag of capacity 10. So let me just abbreviate this MV10. And to find the maximum value in a bag that can hold 10, we have to start by putting in one of these items. So we can put in item A, which has a value of 1 and leaves us with a capacity of 8. So we're going to need to calculate max_val of 8. Or we can put in item B, which weighs 3 pounds, and so we'll have to find max_val of 7. Or we can put in item C, which weighs 4 pounds, and we'll have to find max_val of 6. And to find max_val of 8, we'll need to calculate max_val of 6, and max_val of 5, and max_val of 3. And to calculate max_val of 7, again, if we put in A, we're going to have to make a call to find max_val of 5. If we put in item B, we'll need max_val of 4. And if we need item C, we'll need to do max_val of 3. And for max_val of 6, we'll need to calculate max_val of 4, max_val of 3, and max_val of 2. And to find max_val of 6, we'll have to do, let me stop writing MV so we have more space, we'll need to do 4, 3, and 2. And for 5, we'll need to do 3, 2, and 1. And for 3, we'll need to do max_val of 1. And we could put in item B, which would fill up our entire capacity, so we'll have to do max_val of 0. We can't put in item C if our capacity is only 3. And so for 5, we'll have to do 3, 2, 1. And for 4, we'll have to do max_val of 2, or 1, or 0. And max_val of 3, we can do 1 or 0, and so on. And so you can see our recursion tree is going to be pretty big, right? Now we only have 3 items in our inventory. If we had 10 items in our inventory, each of these would have nominally 10 branches, right? And each time we go one level deeper in the tree, we get another added on amount to our exponent, right? So it would go from 1 to 10 to 100 to 1,000 branches. So this tree grows really, really quickly. And if we try to just do this computationally, it's going to take way too long to actually get a solution. But we have this um, overlapping substructure, overlapping subproblem situation where max val of 5 is being calculated here and being calculated here. Max val of 6 is being calculated here and here. Max val of 3 we're calculating a bunch of times. Right? So for a larger capacity and for more items in our inventory, we're going to see a lot of overlapping subproblems. And so this is a case where dynamic programming would help us, because the first time we calculate max val of 3, we'll save it, and the next time we want to calculate it, we'll just read it out of our cache. We won't have to make these calls to find max val 3 over here. And once we've calculated max val 6, we won't have to go down this whole tree again. We'll just read that value out of our cache. So that works really well. So that's the knapsack problem, and this will give us the maximum value that we can extract from our bag, but it will not tell us what the inventory is, what the set of items are that give us that maximum value. So let's take a look at how we would actually do the housekeeping to keep track of not just the maximum value, but also the inventory itself. Alright, so let's dig into how we can actually track the inventory, and then we're going to go through a few more examples of dynamic programming, but not in as much detail. So this will be the most detailed one. We've already looked at the algorithm in detail. We looked at the call tree. Let's look at how we would actually track the inventory itself. And you may see this in a programming assignment in this course, so this is worth paying attention to. So I'm going to use pieces of paper to represent our call frames, and every time that we make a recursive call, remember we save the previous value of variables. They get saved on the stack automatically for us, and we kind of start from scratch. So I'm going to use pencil and paper, or pen and paper, to keep track of that information. So we want to find the maximum value for a bag with capacity 10, and we're going to use this inventory of items. So there's the weight and there's the value, and so we've got 3 items, so we have to make 3 calls. So let me relabel these: item 1, item 2, and item 3. Alright, so item 1 is worth $1, and we have to find max val of 10 minus the weight of that 2, so we have to find max val of 8. Item 2 is worth $9, and we have to find max val of 10 minus 3 is 7. And item 3 is worth $13, and we have to find max val of 10 minus 4 is 6. Alright, so now we have to make a recursive call to the max val function to find max val of 8. Alright, so now we're going to call max val with an argument of 8 and try to find what that maximum value is. So we could start with item 1, which has a value of 1, and we need to find max val 6. We could start with item 2, which has a value of 9, and we need to find max val of 5, right? 8 minus 3. And we could start with item 3, which has a value of 13. It weighs 4. Our original capacity was 8, so we have 4 pounds left over. Alright, so to do this, we need to find max val of 6. So we're going to make another recursive call to the max val function and say, hey, let's find max val of 6. Well, we could start with item 1, it's worth $1, leaves us 4 pounds of capacity. We could start with item 2, worth $9, leaves us 3 pounds of capacity. And we could start with item 4, $13, and leaves us 2 pounds. Alright, well, we got to find max val of 4. So max val of 4, we can start with item 1, it's worth $1, leaves us 2 pounds. Start with item 3, $9, leaves us 1 pound. Or start with item 4, which is $13, and leaves us 0 pounds. Well, max val of 0, that's a base case, right? So if your bag cannot hold anything, the maximum value you can store in there is 0. So 13 plus 0 is 13. Alright, and if our capacity is 0, we can't store any of our items in there. But this solution here we get by solving the problem for a capacity of 0, that's this, and then adding 1 of item 3. So the solution for a value of 13 is 0 of item 1 and 2 and 1 of item 3. Oh, and sorry, we're trying to find max val of 4 here. All right, well, we need to find max val of 2, so we make another recursive call, and we say, let's find max val of 2. Well, we can put in 1 of item 1, and that leaves us a capacity of 0. And we cannot put in item 2 or item 3 because they weigh too much. Okay, well, what is max val of 0? It's 0, and we get that by putting in none of our items. And so this line here is what we get by solving the problem for a capacity of 0 and putting in 1 of item 1. So we increment this to 1, and we can't put in item 2 or 3. So what's our absolute maximum value? It's this right here. So item 1, we have 1 plus max val of 0. This is worth 1. These solutions don't apply. This is our maximal value. So max val of 2 is equal to 1, and the inventory is 1, 0, 0. All right, we can make our first return from our max val call. We tried to find max val of 2, and we found out it's equal to 1, and the inventory is 1, 0, 0. All right, so we're passing around not just the capacity that we want, but we're also getting back the inventory that gives us that maximum capacity. So we have more housekeeping to do here. All right, so max val of 2, or max val of 4 in this case, put in item 1 and get the capacity of max val 2. So max val 2 is equal to 1. 1 plus 1 is 2. And this solution we get by putting in 1 more of item 1. So this was the inventory that gave us max val 2. And this line says, okay, and we're going to add 1 more of item 1. So there's the inventory that gets us this maximum value of 2. Right? And this is simply saying, hey, if I have a capacity of 4, right, I could put in 2 of item 1. Right, that would weigh 4 pounds. It would be worth $2. There's 2 of item 1. There's the value we get, $2. All right, so we need to find max val of 1. So suppose we have a bag with capacity 1. Well, we can't put in item 1 because it weighs 2 pounds. We can't put in items 2 or 3 because they weigh 3 and 4 pounds also. So there is no item we can put in our bag. So the maximum value for capacity of 1 will be 0. And we get that by putting in none of our items. So now we come back here. Max val of 1 is equal to 0, which we get by putting in no items. So if we start with item 2, we get a value of 9 plus 0 is 9. And the inventory that gets us that was this inventory for max val 1, but we bump up the count of item 2 to a 1. Okay, now we've got 3 solutions for a capacity of 4. What's the largest of these? The largest is 13. So the max val for a capacity of 4 is 13, and the inventory that gets us that is 0, 0, 1. All right, well, we just solved max val of 4. So we know max val of 4 is equal to 13, and the inventory that gets us that is 0, 0, 1. So in this first case, we can get 1 plus max val of 4. So 1 plus 13 is 14, and we get that solution by solving max val of 4, but adding 1 more of item 1. So there's the inventory that gets us a value of 14. And we can sanity check this, right? If our capacity is 6, we can put in item A and item C, items 1 and 3. That'll weigh 6 pounds, and the value will be 1 plus 13 is 14. All right, max val of 3, I don't think we've computed yet. So let's make a recursive call and find max val of 3. Well, we can start with 1 of item 1. So the value of item 1 is 1, and we can add max val of 1. Or we can put in 1 of item 2, which is worth 9, and add max val of 0. Okay, max val of 0 is 0, which we get by not putting in any items. So if we start with item 2, we get 9 plus 0 is 9, and we bump up the count of item 2 by 1. Max val of 1, we found a maximum value of 0 with no items. So max val of 1 is 0 with no items. And so if we start with item 1, we get this, and 1 plus 0 is 1. And item 3 won't fit if our capacity is only 3. And so here's our optimal solution for a capacity of 3. The maximum value is 9, and the inventory is 0, 1, 0. So we're solving the max val function for different capacities, but each time that we solve it, we're writing down in our cache, right, for that capacity, here's the value, here's the inventory. So the next time we need max val 3, we're not going to do all of this stuff. We're just going to say, hey, max val is 9, there's the inventory. All right, so let's go back to the recursive calls we were making. We were trying to find max val of 6. And we said max val of 6 could be 9 plus max val of 3. Well, max val of 3 is 9, and there's the inventory. And so if we start with item 2, we can have 9 plus 9 is 18. And we get that value by taking the solution for max val 3 and bumping up the count of item 2. And then our last case to consider for max val 6 would require max val of 2. And hey, we've already computed max val of 2. Max val of 2 is 1, and the inventory is 1, 0, 0. So 13 plus 1 will give us a value of 14, and we get that by solving max val of 2 and adding an extra item 3, like that. So which of these is our maximum value? It's this case in the middle where we start with item 2. So max val of 6 is 18, and the inventory is 0, 2, 0. All right, so we've solved our max val problem for a number of values already. Let's go back and look at what we were trying to do originally. We were trying to find max val of 8. So we said, okay, first we need to find 1 plus max val of 6. Well, max val of 6 is 18, and the inventory is 0, 2, and 0. So if we start with item 1, we get 1 plus 18, this is 19, and we bump up the count of item 1. So there is a solution for a bag of capacity 8. And it says, hey, we can put in 1 of item 1, 2 of item 2. So that'll be 2 plus 6 is 8 pounds. And this will get us 9 plus 9 is 18, plus 1 is 19. All right, we could also try putting in item 2, and that leaves us a capacity of 5. And I don't believe we've calculated max val of 5 yet. So let's do that. So if we have a capacity of 5, what's the maximum value? So you can fast forward if you've got the idea here. Well, we're going to take this out to its conclusion just to say we did. So if we have a capacity of 5, we can start with item 1, which is worth 1, plus max val of 3. We can start with item 2, which is worth 9, plus max val of 2, or item 3, which is worth 13, plus max val of 1. All right, well, what is max val of 3? So if we have a capacity of 3, the maximum value is 9, and the inventory looks like this. Add an extra of item 1, and 1 plus 9 is 10. If we want max val of 2, max val of 2 is equal to 1, and the inventory is 1, 0, 0. And so 9 plus 1 is 10, and we bump up the count of item 2. or 13 plus max val of 1. Max val of 1 is 0, and 13 plus 0 is 13, and we bump up the count of item 3. And so 10, 10, 13, here's our optimal solution. So max val of 5 is 13, and the inventory is 0, 0, 1. Well, now that we know max val of 5, we can go back here and fill it in. Max val of 5 is 13, and the inventory is 0, 0, 1. 9 plus 13 is 22, and we bump up the count of item 2. And then finally we have 13 plus max val of 4. Well, look in our cache, max val of 4 was 13 with an inventory of 0, 0, 1. And if we bump up the count of item 1, we get 2 of these. 13 plus 13 is 26. And what's our best solution here? Start with item 3. So max val of 8 is 26, and the item count is 0, 0, and 2. Alright, now we've just completed our first recursive call that we made in trying to find max val of 10. Because we know max val of 8 is 26, and our inventory is 0, 0, 2. And if we add item 1, we get 27 with a count like this. Alright, we also need to find max val of 7. So let me reuse this sheet. Let's find max val of 7. And we'll just remember max val of 1 is 0. So max val of 7. Well, it could be the value of item 1 plus max val of 5, the value of item 2 plus max val of 4, or the value of item 3 plus max val of 3. And I believe we've got all of our required recursive values calculated now. So max val of 5 was 13 with an inventory like this. 1 plus 13 is 14 for that inventory. Max val of 4 was also 13 with an inventory of 0, 0, 1. And so 9 plus 13 is 22. Bump up the count of item 2. And max val of 3 was 9 with an inventory of 0, 1, 0. And so 13 plus 9 is 22, and bump up the count of item 3. So which is our optimal solution? Well, it could be either of these. But these are exactly the same solution, right? Max val of 22, same inventory, 0, 1, 1, 0, 1, 1. Our code would pick, maybe the first one that it finds that's bigger than what we've seen so far. But it doesn't matter. These are both going to give us the same answer. So for capacity of 7, max val is 22, and the inventory is 0, 1, 1. Okay, so now we can complete the second recursive call from our original function where we found max val of 7 was equal to 22, and the inventory is 0, 1, 1, and we're bumping up the count of item 2, and 9 plus 22 is 31. And then our last possibility uses max val of 6. Well, max val of 6 is 18 with an inventory of 0, 2, 0. 13 plus 18 is 31, and we bump up the count of item 3, so we get that. And again, these are our maximal solutions. So max val is 31, and the inventory count is 0, 2, and 1. And if we go way, way, way back to the beginning of all of this, right, this was our original problem, and capacity was 10, and by kind of playing around with the numbers, we found out, hey, putting 1 of item 3 and 2 of item 2 gets us our optimal value of 31. Well, that's what we just discovered algorithmically. Put in 2 of item 2, 1 of item 3, we get a capacity of 10, can give us a value of 31, and that's our optimal solution. All right, this was a lot of work for us to do by hand. This is child's play for a computer, of course, right? It's a simple for loop. Iterate across each of your items, and for each item, add its value plus the maximum value of your bag with the capacity reduced by the weight of that item, and then pick the largest of those calculations. That's your maximum value, and just keep track of your inventory. All right, so that's the knapsack problem. And it works really well with dynamic programming because, you know, every time that we wanted to calculate max val of 3, we just came here and we read out, oh, the maximum value is 9, here's the inventory, instead of repeatedly going through, you know, these calculations. Anytime that we need max val of 5, we can just say, oh, it's 13, here's the inventory, instead of doing these calculations. And the savings, if you had a large inventory and a high capacity, the savings are incredible. Right, this makes the problem completely doable in a short amount of time. All right, so that's the knapsack problem, and it's similar in spirit to a number of other problems. So, second problem to talk about is what we can call rod cutting. And here's the idea: we have a piece of metal, and we can cut this into a number of pieces. So let's say this has a length of 1, 2, 3, 4, 5, 6, 7. And we could sell this 7-inch piece of material for a certain price, but it may be that if we were to cut it into a bunch of 1-inch pieces, we could sell that for more total money, right? Because there's value in getting something cut to length. So we have a pricing table with length and value. Right, and there's some value for each length, and the question is, how should we cut this rod up to sell it to get the maximum value? Because maybe, you know, there's a high demand for 3-inch pieces of steel, and if we cut it into 2 3-inch pieces, maybe we would get a lot more value than if we just sold it as a single 7-inch piece or a 6-inch piece and a 1-inch piece. And so we can say maximum value of length equals the largest of, well, the value of a 1-inch piece plus the maximum value we can get from the remaining 6 inches, or the value of a 2-inch piece plus the maximum value we can get from 5, and so on, all the way up to the value of a 7-inch piece plus the maximum value of a 0-inch piece, which is just 0. So it looks a lot like the knapsack problem, right? We have an inventory or a pricing table of values per length, and we simply say, hey, the first piece you cut off is going to be, you know, 1, 2, 3, 4, 5, 6, or 7 inches, right? And so in each case, we have the value we get from that piece of material plus whatever the maximum is we can get by cutting up and selling the remaining length of material, and we find that maximum value by calling the same max val function that we're describing here. So very recursive, optimal sub problems, right? If we can solve these problems and find the maximum value, then we can find the maximum value of a rod of length 7. So that's the rod cutting problem. All right, a problem with a slightly different feel is longest common subsequence. And the idea here is, suppose you have 2 strings. So So this pops up in analyzing DNA, for example. You may have two sequences of GATCs, and you want to know what's the longest string of characters that is common between these two sequences. And, you know, if we just kind of look side by side, well, there's a TA and a TA, so there's a sequence of length 2. And, you know, there's another TA that might go with that, and so on. But if we allow for gaps between letters, right, it's hard to just kind of eyeball this and know what's the longest string that's common between these two. And so, for example, you know, here's a G and a G, here's an A and an A, here's a TA and a TA, and then we could skip over to this T and this T and this A and this A, and there's a C and a C and an A and an A. So there's a fairly long string of characters that's common between these two strings, but it's not obvious, right? And we can solve this problem exhaustively by just trying, you know, all possible combinations of pulling letters out of here in order and letters out of there and comparing them. But computationally, that's a really, really complex problem, right? Simple to code, but it would take a really long time to run. But we can use this idea of overlapping subproblems and suboptimal solutions, and we could write an algorithm for longest common subsequence of two strings. And so let me introduce a bit of notation. So A prime equals A with first character removed. So if A equals, you know, GATCA, A prime equals ATCA. So this is just an abbreviation for a string when we chop off the first character. So if we want to find the longest common subsequence of two strings A and B, we can do it as follows. So there's a pair of cases. If A and B have the same first character, in other words, if A and B start with the same character, like in this case, we can simply find the longest common subsequence between these remaining strings and then add 1. Because whatever the longest common subsequence is between these strings, it's certainly going to be a string that starts with a G and is followed by the longest common subsequence of these strings. So we're trying to find the length of the longest common subsequence. So whatever the length is of the longest sequence between these, we add 1, we get the longest sequence of the two original strings. So if A and B have the same first character, we can just return 1 plus that longest common subsequence length of the remaining strings. Else, return the maximum of the longest common subsequence of A, B prime, or the longest common subsequence of A prime, B. Okay, what's the logic here? Suppose that these strings start with something different. Suppose this starts with a T, right? And this starts with a C. These don't have to be the same length, by the way. Suppose these are our two strings, right? Well, it could be that you know, there's some longest common subsequence between these that's also the longest sequence between these two. Or it's going to be the same as the longest common subsequence between these two. But we know that, you know, whatever the longest common subsequence is between these, it's not going to be if we find the longest sequence between these two original strings, right, it's going to be the same as either the longest sequence of these or the longest common subsequence of these, right? Because these two strings do not have the same first letter. So if the longest common subsequence happens to begin with a T, right, then taking off this first letter here is not going to affect it, right? Because it begins with a T, so maybe it's picking up that T or maybe not, but it's not going to begin with a C. And likewise, if the longest common subsequence begins with a C, we don't change our longest common subsequence by removing this T from this first string. So we have two subproblems: either find the longest common subsequence of these or the longest common subsequence of these. And whichever one gives us the maximum value, we return that. That's the longest common subsequence of the original two strings. And in each of these cases, when we call LCS, at least one of these strings is shorter than one of the original strings. So it's a subproblem, right? It's working on a problem that's slightly smaller because at least one of these strings has one character fewer, possibly both. And there's a base case. If A or B are empty, in other words, if they have no characters, return a 0. Well, each time we make a recursive call, at least one of these strings gets shorter. And so after a finite number of recursive calls, eventually one of these arguments will have a length of 0, and our LCS will use the base case and just return a 0. So this will terminate at some point, and we'll start coming back from our recursive calls, and eventually we'll get our answer. And obviously a lot of common subsequences. So, so this is another problem that works well with dynamic programming. Okay, and finally our last example, this is egg dropping. And so this is a kind of bizarre little experiment. Although egg dropping has a good tradition in engineering, a lot of engineering schools have egg drop competitions where you try to design some device that you can put an egg in and drop off from, typically the top of the engineering building and have it survive. And you get graded on how quickly the egg falls, how close it lands to the middle, and of course whether the egg survives. So there's actually some legacy here. So imagine that we have a building and it has a certain number of floors, and you have a basket containing a certain number of eggs. All right, your goal is to figure out what's the highest floor you can drop an egg from without it breaking. And it could be, you drop from the first floor and it breaks, and there the highest floor you could drop from would be 0. Or it could be you can drop all the way from the top floor and the egg survives. And so the setup is, you have a certain number of eggs, certain number of floors. If you drop an egg and it survives, you can use it again. And it doesn't take any damage, so there's no cumulative effect of dropping. But if an egg breaks, you have to discard it. You can't use it again for another experiment. And so what is the optimal number of experiments you can run to determine what's the highest floor from which you can drop an egg? So the question here is not, what is that magic floor number? The question is, what's the number of experiments you need to answer that question, right? So we have a function egg, which takes a number of floors and eggs, and tell us number of experiments which will be sufficient to determine the highest floor from which an egg will survive. And all the eggs are the same, all the conditions are completely repeatable. So if I drop an egg from this floor and it cracks, it's guaranteed every time I drop an egg from that floor it'll crack. It doesn't matter which egg I drop. It doesn't matter what the wind conditions are or anything like that. So a very controlled environment. And so we want to write this function egg, takes the number of floors and number of eggs and tells us how many experiments do we have to conduct. Okay, we could also have it tell us more information, but we're not actually trying to write a function that tells us what's the safe floor, because we don't know, anything about the eggs or the surface and so on. But we're trying to find what's the number of experiments we need. And we're looking for a guaranteed number of experiments. It may be that, we drop an egg off of floor 1 and it cracks, and hey, one experiment answered our question. But it may be that, that in some other case we might need more than one experiment, because maybe floor 1 it will survive. So we're looking for a function that tells us what's the guaranteed sufficient number of experiments. All right. So we're getting pretty abstract here. So let's think about this in a few cases. Suppose you only have one egg, right? Your testing procedure is very simple, because if I drop it from the second floor and it cracks, I'm out of eggs, and I don't know if it would have survived from the first floor or not. So if you only have one egg, you've really got to start from the first floor, second, third, fourth, and keep going up until it cracks. And that could take, F experiments. So if you only have one egg, you don't have a lot of choice. All right, so if the number of eggs is 1, we just return the number of floors. On the other hand, if the number of floors is 1, if your building only has one floor, all we have to do is drop the egg off that first floor. And if it cracks, we know that it will only survive if we drop it, from the ground level. If it breaks, and if it survives, we know that we can drop it from the first floor. So if F equals 1, we can just say, hey, it's going to take us one experiment to answer this question. Otherwise, we got to do some work, and guess what? This is going to be using subproblems. All right, so we've got a basket of eggs, we've got a set of floors. We don't know which floor we should drop it from, right? If I have 2 eggs and I drop my first one from the middle and it cracks, well, I got to start at floor 1 and work my way up, because I've only got 1 egg left. But if I drop my first egg from the middle and it survives, right, hey, I got lucky. I've got 2 eggs, and I know I only have to check these upper floors. So now I can start getting a little more creative. So there's not a clear intuitive solution to this, but here's how we can do this programmatically. So we can say for test floor equals 1 to F. So we're going to imagine what happens if we drop our egg from each of the floors. And there's 2 possibilities. The egg will crack or the egg will not crack. So if the egg survives, so let's say we drop it from this floor right here, and the egg survives. Well, we still have all of our eggs available. We don't have to try dropping it from any of these floors. So this is a 9-story building, so we just dropped it from floor 4 and it survived. We have not 5 floors that we still have to examine. And so we need to look at egg of number of floors minus test floor, comma, and the number of eggs. In other words, if we drop from test floor and it survives, we now have this many floors to explore, and we have E eggs to do that exploration with. So however many experiments we need to solve that problem, right, that's the number of experiments we'll need to solve the original problem. So it'll be, 1 experiment we already did plus this many experiments to solve this subproblem. On the other hand, if the egg breaks, well, we've done one experiment, and if it broke on test floor, now we have to test from the remaining floors below that. So we have to do test floor -1, and we have one fewer egg to work with. All right, and we're looking for a guaranteed sufficient number of experiments. So we want to find the largest of these. Right, maybe if the egg survives, we're only going to need 3 experiments, but if the egg breaks, we're going to need 5 experiments. So to guarantee enough experiments, we have to look at the worst case, which would be 5 experiments. So we're going to find the largest of these, and we simply do that across all of the floors. All right, so when we've finished that, we want to, across all the possible floors, find the smallest. Right, so we start with floor 1, and we say we're going to drop from floor 1. If it survives, we're going to need this many experiments total. If it breaks, we're going to need that many experiments. We have to find the largest of those. And that'll say, okay, floor 1, we can guarantee a total of 7 experiments. Floor 2, a total of 9. Floor 3, a total of 6. Floor 4, a total of whatever, and so on. We find the smallest of those. That's a guaranteed number of experiments that will be sufficient to answer this question. And so we return the smallest of those, and that's the value of our egg function for that number of floors, that number of eggs. So that's about the most abstract version of these examples, right? The goal of these 4 examples has been to give you some different feel for how we can express problems in terms of these common subsequences, subproblems with overlapping structure. The way we would go about coding this is the same in all cases, though, right? The mechanics of coding this is much different from the mechanics of the knapsack problem or the rod cutting problem or the longest common subsequence problem. But the essential part that makes this dynamic programming is the fact that we would be caching our results, right? And as we go through this, we're going to find that we keep bumping into repeated occurrences of this egg function, right? We're going to call egg for the same pair of values again and again and again, right? Especially if we have a lot of eggs and a lot of floors, we're going to find a lot of cases where we have to solve these problems. And by using a cache to save our values when we call them, we'll be able to save a lot of time in the execution. All right, so just to show you some of the outcome of this, if we look at the egg drop problem, for example, we can say, okay, suppose I have 10 floors and 1 egg. It's going to take 10 drops to solve the problem, because you have to start from the first floor and you work your way up. If you have 10 floors and 2 eggs, you can get away with only 4 experiments. And here you can see the subproblems that it solved, right? First it tried to solve 2, 9, 2, 8, 2, 7, and so on. And we don't see, what the experiments are that we should conduct, because that depends on the outcome of the experiments. But we're guaranteed we can answer this question with only 4 experiments instead of 10. And if you have 10 floors and 3 eggs, it's still going to take you 4 drops. And if you have 10 floors and 10 eggs, it's still going to take you 4 drops. So we can't do any better, guaranteed, than 4 experiments. Again, we might get lucky. We might drop from the first floor and it breaks, and hey, we've answered our question in 1 experiment. But the fewest guaranteed number of sufficient experiments in this case would be 4. Now, if we have 20 floors and 2 eggs, it's going to take us 6 experiments. 20 floors with 3 eggs, we can get down to 5 experiments. 20 floors with 4 eggs is also going to take 5. If you have 100 floors and 4 eggs, it's 8 drops. 100 floors and 5 is 7 drops. 100 floors and 6 is also 7 drops. So, you know, having extra eggs at some point doesn't help you. But 100 floors, right, being able to answer that question in 7 experiments instead of, you know, if you only had 1 egg, 100 experiments. So that's a significant savings. So these answers aren't clear to us, and we're seeing, you know, some of the subproblems that are solved. So if we do 100 eggs and we have 100 floors and we have 6 eggs, you can see the subproblems it's solving. So it looks at the case where we drop 1 egg from the first floor and it survives, so we have 99 floors left to check. If we drop from the second floor and it survives, we have 6 eggs and 98 floors to check, and so on. So it's going to have to solve all of those subproblems. But if we drop from the floor and it breaks, then we have 5 eggs, but we only have 2 floors left to check. So that's when we're working from the 3rd floor, and so on. So it will work on all these subproblems and eventually get us our solution. Now this is with caching, so the problem should only pop up once a piece. Longest common subsequence. So we can put in a pair of strings, and it tells us the longest common substring has a length of 7. But we can see, for example, that it solves the same problem multiple times. For example, longest common subsequence between S and AS. It solves it there, and there, and there, and there, and so on. And so here's all the subproblems that it tackled. And this did not employ dynamic programming. So it solved, you know, it called the LCS function a lot, but it spent a lot of time working on the same pairs of strings. So if we use dynamic programming and we save our substring solutions, we save, even with these longer strings, we only called it, you know, a handful of times. And each of the problems it solved was only solved once, and it eventually let us find the longest common substring. So, those are examples of how these functions behave in practice. All right, so that's dynamic programming. So you have practice problems where you're basically going to explore some of these problems with sample inventory tables and try to get some experience with breaking these problems down into subproblems and caching the results yourself and thinking about how you would cache them in a computer. And then you'll probably have a programming assignment this quarter that will require you to code one of these problems. So we'll get into the details of that separately. All right, thanks. Bye.